And we're starting with our first paper talk, Maximal Simplification of Polyhedral Reductions. And our speaker is Luis Narmour, affiliated with many institutes, including Colorado State University. So yeah, I'm excited to hear that. Thank you.
Great. Everybody can hear me all right? Okay, cool. So my name is Luis Narmour. So part of what I want to talk today about is work that came out of my PhD. So I did a joint degree between CSU here in Colorado and University of Rennes in France. So I spent 2 years in France as part of doing this. So let's just dive right in. Okay, so I want to start with a simple example, and this is probably going to be something that a lot of you have seen, but just bear with me because it illustrates all the things that I want to talk about. So I mentioned we're talking about this program transformation called simplification, and the prefix sum is the simplest example of simplification. So imagine I give you some loops like this, some doubly nested loops, and we want to produce this output array y from this input array x, where the ith element of the output is the sum of the first I elements of the input. So if we just think about what this is doing, you can imagine we have some space, some iteration space of the values that the iterators can take I and j. And imagine we align the input array x along the vertical here and the output array y along the horizontal. And then if we just think about what this is computing, to produce the first element of the output, we just sum the first element of the input 7. Then to produce the next value, we do 7 plus 5, and 7 plus 5 plus 2, and so on over the course of the whole thing. Now, what this means is that we would say that these loops have a quadratic complexity. But if you look at this for any more than a few minutes, you'll say, okay, well, you're kind of redoing a lot of work. So once we produce one answer, there's no reason to resum a lot of the same elements. In other words, once we have the answer in the fifth place here, once we have 18, there's no need to resum 7 plus 5 plus 2 plus 3 plus 1 plus 8. We have everything we need in order to produce the value from 26 by just taking the previously computed value and incorporating the only new, not yet seen answer. So what this lets you do is it lets you re-express the same computation in a more efficient way. So we can compute the same thing in now a linear time algorithm. So if you forget everything else that I say, this in a nutshell is the simplification transformation. So we want to go from some specification, like what you're looking at on the left, whether it's loops or equations or something like this, and identify when there's this redundancy, when there's this reuse that can be exploited, and automatically rewrite the program representation in a cheaper, more efficient form. So I had three words. I had simplification of polyhedral reductions. So just to kind of set the stage for the context of what we're talking about, reductions, we're talking about computations that combine collections of inputs, often with an associative or commutative operator, to produce one or more results. And so these things, think accumulations. These are ubiquitous. They appear all over the place. We see them in RNA structure prediction in bioinformatics. We see them in tensor contraction networks using quantum chemistry. Deep learning these days is all the rage. The backpropagation layers, these matrix multiplication, these matrix products are themselves reductions. And these are interesting in the sense that even the OpenMP, the C++ multi-threading library, has a whole series of pragmas and directives dedicated just to parallelizing reductions. So there's all sorts of things that you have to do to be clever with these things. So what I'm talking about here, we're going to do some of this analysis based on polyhedral compilation techniques. And when I use the word polyhedral program, really what I'm talking about are these iterative computations that typically have static affine control and data access. So what I mean is, you think about these loops. This is the same prefix sum example that I showed you at the beginning. We have this iteration space that's defined over this triangular domain, and we think of each point inside this domain as having some computation. And we can write this set of points, I and j, that comprise this domain in a nice closed form as a set of finitely many inequalities. So we have this domain that describes the iteration space. Similarly, we have a data space for each of the variables. So for the input variable x and the output variable y. In this example, they're both 1D, and I'm showing x to be along the j-axis and y to be along the y-axis. And then you think of variable axes as affine functions from the iteration space to the data space. So what I mean is, inside the body of this loop body, we have an array on the variable x that accesses, at each point ij, we read the point j. So we can describe the axis on x as the function from ij to j. And these are relations, so we can describe them as arrows. So at each point inside this triangle, we read some value from x along the vertical, and we accumulate it into the location on the floor. So polyhedral programs, iterative computations with static affine control. And a polyhedral reduction is everything I just said, plus we think about all the rights as being accumulations. So we have plus equals, or max equals, or op xyz equals. Now, the problem that this paper that did this work solves is, given some polyhedral reduction as input, can you rewrite it with a lower and ideally optimal asymptotic complexity? So I give you some loops like this, some loops with 4 levels deep, and can you rewrite for me an equivalent version that is cubic, quadratic, or linear? And you can. And so the answer, so this is, there's this simplification came around, or was introduced in 2006, and they addressed this problem. So being able to take an input specification like the 4 loops on the left here, and automatically spit out the equivalent quadratic representation without having to use your clever human to say, oh, I recognize that we're reusing things like this. And the nice thing about this is that it's systematic and automatic, meaning it doesn't take some clever human to look at it, and it's optimal in the sense that I can guarantee that there's a quadratic specification that computes this program, and simplification can find it. So part of this work is about addressing some of the limitations, because while it's a powerful technique, it has some limitations. So the prior work on this was largely theoretical, and it sometimes fails. So if you take these loops as simple as this 4-nested loop body, and you change it so that now we're using an operator like max or min, this example is hilariously difficult. So if you want to appreciate why or the difficulty here, take these loops and write it in Python or C or something, and try to express the same computation with quadratic complexity. It's laughably difficult. We spent weeks just trying to show that you could do it. But everything that I'm talking about today sort of gets us there in a systematic and automatic way. So now, to be a little bit more formal, or to talk about what this redundancy, this reuse that's baked, how do we remove the redundancy? Simplification characterizes this notion of reuse, which is it's a linear set of points that read the same value. And again, we're in the range of, we're in the umbrella of polyhedral compilation, so we can model these things as affine spaces. And in this example, what we have here is that we have a read function on x. That's the function ij goes to j. And the null space of this is what I mean when I say the reuse space. The null space of this function is what characterizes the set of points that read the same value. So pictographically, what that means is our function ij goes to j. The null space is the horizontal space along the i-axis. And what that means is if we look in our picture here, if I plot out all the points that are being read, that's why we have the values that appear in the same, we have rows of the same value. So a way to think about this is at any point inside the iteration space, if you walk along the reuse space, we're reading the same value. So the whole point is that we have a nice, precise way to characterize this. Now, since we're talking about the polyhedral model, this leads to a nice, pretty geometric picture that I can draw and illustrate. So when the reuse space is non-empty, in other words, when we have some loop body where we read and accumulate expressions inside the body with a function that has a non-empty null space, we say that simplification can take place along some choice of reuse in this space. And pictographically, what that means is, again, let's let D be our iteration space, so the triangular region here. And I'm going to say, okay, pick some reuse vector in our reuse space. So again, we have the I-axis as our space, so we have 2 choices. We can either go from right to left or from left to right. And here I'm just going to pick arbitrary from left to right. And the way you can visualize this is imagine we take our domain and we shift it along row to yield some new domain. And now throw out everything in the intersection. So all the points where the two triangles overlap, that sort of encodes the redundancy. And now we think about the computation as only being defined over these residual, the places where they don't intersect. So over some of the facets, some of the edges of this. And again, not all of these contribute because remember that our output is along the horizontal and everything gets projected onto the output. So not all the points, some of the points under the projection land in spaces that aren't defined. So the whole point is we have a residual computation defined over some of the facets. And then once we have that, we have a way to rewrite the same computation. So all that I'm trying to illustrate here is that now we just think of this new computation, these loops, as being defined over the points that are just along this top red bar. And we say that you can think about this as having a linear complexity because the number of points inside the edges are linear, and the number of points inside the triangle is quadratic. So think about the computation as being moved over the body of the triangle, i.e. quadratic, with quadratic complexity, to just some of the edges, linear. So this choice it's not at all unique. There's multiple ways to do this. So I just showed you going from left to right. And imagine we sort of think about the same thing where we go from right to left. And all that I mean is we're using the value in the answer produced from either the left or right to produce the next one. So pictographically, imagine we do the same thing. Now we shift our red triangle from right to left, throw out the intersection, evaluate just the residual computation over the sum of the facets, project out the ones that don't have an answer in the output, and now we have a different, yet another linear time program representation that computes the same thing. And the way to think about this is instead of starting from the left and incrementally adding one thing, first we do an initial summation of all the points on the very right. We produce the very rightmost answer. We produce that 29. And then we take 29 minus the previously thing, the values that were used to produce the last element in the output. And we subtract, you can't see it here, but you see it was 3 on the top. So we go, to get 26, we go 29 minus 3 gives us 26. So the whole point, there's the choice in which we decide to exploit reuse is, there's multiple choices. So at this point, in general, there's many choices. In this example, there's 2. So for the rest of what I want to talk about, I'm not going to show any code or any points or anything like this. I just want to pass, I want to describe, think about these computations, these programs as these pictures. So we have some domain, D, and a reduction defined over it, accumulated by this big O plus operator. And we say it has a non-empty reuse, and simplification exploits one choice of reuse and pushes the computation onto some of the facets. So we have a residual computation that looks like what you're looking at on the left, where we have points over just the top oblique, accumulated by the operator itself, big O plus, or the inverse, where we exploit reuse from right to left, what you're looking at on the right-hand side. Now, the crux of where this paper comes into place is that not all choices of reuse are possible. So imagine that the operator doesn't admit an inverse. So if we have something like min or max, there's still 2 ways to exploit this reuse, but there's no way to there's no way to write the loops for the equivalent computation on the right-hand side here because there's no unmax operation. So what that means is among the choice, we have to throw some of them away, and there's only one that's actually legal. And that's not a problem for this example, for the prefix sum, or for the prefix max in this case, because among the 2 choices of simplification, there's one that exists that doesn't use the inverse op. So we're fine. But you can imagine that in general, when all choices of simplification, all choices of reuse involve the inverse op, simplification as it was produced from 2006 fails. So imagine we have some computation that looks like this parallelogram here, where we have, we're accumulating points along this sliding sliding window going up. And the question is, can we still develop a lower complexity linear time algorithm here? And of course we can. That's why I'm here. So the key observation is that we can split this into two pieces and simplify each piece independently, because these operations are commutative. So imagine we split this parallelogram or this domain into two pieces, and now we have this upper triangular piece where we can exploit reuse from left to right, meaning produce the next value in the answer from the previous answer computed on the left, and then we do the exact opposite below. And the whole intuition that I want to pass here is that these right triangles are important. So these are prefix scans or suffix scans. So another way to frame the problem that we're solving here is, given some reduction defined over some 2D polytope, can we figure out how to split it into right triangles? And of course we can. Triangulation, we do this all the time, right? So some shapes, just to sort of pass the intuition, some shapes can be right triangulated in a super straightforward manner. We can split this shape into right triangles like this, and every rectangle you can think of as two right triangles, so just forget those for now. But the whole point is, now we have these pieces, and we can simplify each piece with a unique choice of reuse. But this becomes complicated. So imagine we have a shape that looks like this. Can you fill up this domain with right triangles? And you can, but the challenge is that there's an unbounded number of splits, because n is parametric. So how can you use this to transform the program in a way that doesn't require us to repeatedly split here, split. And the thing is that after two splits, so when we're working with triangles, we have everything we need in order to guarantee that a repeating pattern always occurs. And what this leads to a simple, quote unquote, recursive cogeneration strategy where we have this reduction defined over this triangle. Two splits, we make one choice of reuse from left to right on this top right triangle, and then we do the opposite on the bottom right triangle, and then we recurse into the blue region. And then this leads to a cogeneration strategy that has linear time complexity. So an interesting observation that came out of this work is that, surprisingly, the 2D case is hard, but the higher dimensional case is easy. And this is usually the opposite of what we see. Normally we add another dimension and we encounter some combinatorial explosion of the search space, and we have to encounter all these things. But the higher dimensional analog of sort of decomposing a polytope into quote unquote right simplices is easier. And again, I don't have time to talk about all this now, but a lot of the paper is dedicated to proving that we can do this always in a finite number of splits. So I'm talking about what's a hypertriangle is a simplex, so think of it as a tetrahedron. And you can think about it as the convex combination of d plus 1 vertices. So a pyramid is 4 vertices. And the notion for what I want to call a right simplex is it has an edge that is parallel to one of the axes. And again, I'm being very hand-wavy here because I'm just trying to pass the intuition that what we're trying to do is, given some input domain like this, can we figure out how to cut it up into sort of right simplices such that each piece is easier to simplify? And sort of what we do is we have a bunch of, it's not really a heuristic, but we have a way to guarantee that by splitting these things through their edges, so splitting a D simplex through its D-2 face gives us a way to produce two smaller, easier to simplify pieces in such a way that we can guarantee that this process terminates. So a lot of the paper is dedicated to the math and giving constructive proofs to show that this always works. And what's interesting about this whole thing is the 4D example that I showed on the first slide, where I said this example is hilariously difficult. It's fun to work through because, I shouldn't say it's fun, but there's no way to avoid all of the things that I've talked about so far. So you have to consider how do you split this 4 simplex, this 4-dimensional polytope into smaller pieces. And then among all the residual choices of computation, we have these triangles where you can't avoid this needing an infinite number of splits. So I have 2 more slides, and the only other thing that I want to mention is that, so we have an artifact with this where you can play around with this. It's a proof of concept implementation of a lot of the key components. So you can write input equations that have some quadratic complexity, you can push the simplification button and it spits out an equivalent linear time program. So all you need to use the artifact is a Linux machine or a Mac machine with Bash and Java 11. In the artifact, we link to the whole source code for the underlying the Alphas toolchain. It's implemented in Java using the Eclipse modeling framework and all these things. If you would like to play with it, just come find me. I'm more than happy to chat about it. But this is free for you to play around with and break it and try to see what you can do. And there's always more work that can be done. So everything that we talked about here are sort of simple independent reductions. But there's still this combinatorial explosion of the search space that we need to figure out how to do. And there's sort of additional optimizations that you can think about as how do we characterize the sort of families of simplifications that fall out. So, thank you.
So maybe time for one quick question while the next speaker prepares a notebook. Yes?
If you take the product of matrices, you have an algorithm, and then you say, I consider now triangular matrices. So are you able to get the specialized code for triangular product of triangular matrices?
So just triangular matrix multiplication, there's no reuse baked in the computation. But if you imagine you have like a matrix chain product where you have A times B times C, there's reuse baked into that implicit program representation, and the tool can find it. It does spit it out using this exact kind of analysis.
Okay, so let's thank our speaker again. And